All right, section 8.1 on the law of sines. All right, section 8.1, we're going to move beyond the right triangle. Okay, so far, everything that we've been able to do with trigonometry as far as word problems goes, applications, has relied on us being able to impose a right angle somewhere in the problem. Like the tree had to be perpendicular to the ground or the building, something like that. Because the only tools that we had were the Pythagorean theorem and then our SOHCAHTOA. Okay, sine, cosine, and tangent. All of those things rely on there being a right angle in our diagram. Okay, so if we don't have a right triangle, then we have what we call an oblique triangle. It's just a triangle with no right angles. All right, and some notation in this section and in the next one that we're going to use. The angles, we're going to use the first three letters of the Greek alphabet. We're going to use alpha for one angle, beta for another angle, and then this one is gamma. We haven't seen this one yet. And gamma kind of looks like a swoopy Y when I write it. It kind of looks like that. And then the side lengths, we're going to use A, B, and C. But it's important to note that side A is always opposite angle alpha, side B is always opposite angle beta, and side C is always opposite angle gamma. All right, so we don't have a hypotenuse. It's not important which angle or side length gets labeled with which letter. It's just that association. Alpha has to go with A, beta with B, gamma with C. All right, and we're going to be interested in solving these oblique triangles. Okay, so maybe this triangle here, maybe this side length A is the distance across a lake, and maybe with survey equipment we're able to know the measure of this angle alpha and these two side lengths here. Okay, so we want to be able to solve for the unknown side length or maybe an unknown angle. Okay, and there's lots of different ways that we could get the information that we need. We could possibly know two angle measures and any side length. Okay, so this is like the minimum amount of information that we need to solve this triangle. Okay, so we might know two angles, so I might know the measures of angle alpha and angle beta, and then any side length. Okay, so I know those two angles. I could know the side length that's sort of between those two, or I could know one of these side lengths that's not between the two. Okay, so we call that case angle, angle, side, or angle, side, angle. Okay, so angle, angle, side would be where we know angle, angle, and then a side that's not between them. Okay, so that would be angle, angle, side. Angle, side, angle would be where you know the side between them. Okay, and those two situations are pretty much the same. Okay, so if you know those three things, two angle measures and any side length, then you can solve the triangle for the rest of the things you don't know. All right, you could also be in the situation where you know two side lengths and an angle opposite one of them. Okay, so this is going to be the side angle. This is where you know two side lengths, so maybe I know these two, and then an angle opposite one of them. So that would be, if I know A and C, then I would know alpha, or maybe I might know gamma. All right, so that is the side angle. That's different from side angle side, where if I know A and C, I know beta. That's a different case. All right, you can solve an oblique triangle if you know all three side lengths. Okay, so if you know A, B, and C, and you don't know any angles, we'll be able to solve that with one of our formulas. And finally, we'll be able to solve an oblique triangle if we know two side lengths and the measure of the included angle. This is what we call the side angle side. Okay, so this is where we know a side, and then the angle in between them. All right, we solved that one differently from the side angle that we were talking about earlier. All right, so you have four different cases that you might be in that you can solve an oblique triangle. All right, so the angle, side, angle, and so on. If you're in one of the first two bullet points, angle, side, or angle, side, angle, or side, angle, we're going to use the law of sines to solve those triangles. If you're in the other two cases, we'll be using the law of cosines. All right. We're actually going to skip the side-side angle. That one is kind of difficult. That is where you're using the law of sines to solve for an angle. All right, and that can get kind of complicated. We call that the ambiguous case. And it just takes a really long time to go over all the things that can happen when you're solving an oblique triangle in the side-side angle case using the law of sines. So we're going to skip that, and we'll just do the angle, side, angle with the law of sines. All right, and then we'll use the law of cosines in the next section to solve side, and side, angle, side problems. All right, and so let's see. So let's actually get to the law of sines. Okay, so the law of sines, let's see. And so the law of sines states this. All right, it's really kind of an equation. It's got three parts to it. And you're only ever going to use two parts at a time. So you might have a problem where you're using just this part. So let's just kind of focus on that red box. All right, that red box says that the side length A divided by the sine of angle alpha, and remember those two are sort of paired together in the notation, right? So if you've got side length divided by the sine of its partner angle, that ratio holds all the way across the triangle. That's the same as taking side B and dividing it by the sine of angle beta. All right, and again, you could be using this with, you could just be using the B and C part of the formula. You're never going to use all three parts of the law of sines at the same time. All right. And that's the one that we're going to be using when we're solving when we're solving angle, side, and angle, side, angle. All right, it's also worth noting that you can actually write this formula using the reciprocal. Okay, so we said this one was good for angle, side, and angle, side, angle. If you were using the side angle, which again I said we're not going to do in this class, you would want to use this version. That's basically just flipping these fractions over. So when you flip the fractions over, they're still equivalent to each other. All right, but we're going to focus on this version here, where we're going to use the law of sines to solve for a missing side length. All right, so we'll keep that in mind. All right, so our first example 1 tells us to draw a triangle, and it gives us a couple of angle measures and a side length. Okay, and then they want us to find the measure of the missing angle and the remaining side lengths. So we're going to solve an oblique triangle. Okay, so we don't have to be exact. You don't need to bust out a protractor to get this right. We've got a 102 degree angle, 102.3. So just make sure it looks like it's bigger than 90 degrees. Okay, so this is going to be my gamma. All right. And let's see, let's label that gamma up here. And then angle beta is pretty small, 28.7, so I'll put that over here. And even if your diagram isn't perfect, as long as you label everything correctly, you're going to be all right. All right, and then they also tell us that side length B is 27.4. Remember that side length B has to be across from angle beta, so that has to be this side over here, 27.4. All right, and it wants us to find the missing everything. All right, so because I labeled the top angle gamma, that means that this missing side length down here has to be side length C. Okay, side length C goes across from angle gamma, and the only thing that I have left, this third angle over here, has to be angle alpha. That's the only Greek letter I haven't used yet, and that has to be across from side length A. All right, so we need to find angle alpha, side length A, and side length C. All right, so angle alpha is going to be the easiest one. We don't actually need to use the law of sines for this one. Angle alpha is just the third angle in the triangle. Okay, so remember that there are 180 degrees in a triangle, and we've used up 102.3 of them for gamma, and we've used up 28.7 of them for beta. So I'm going to do 180 on my calculator minus 102.3 minus 28.7, and I get 49 degrees. All right, so let's see if I can squeeze that in there. 49 degrees. All right, now to find side length A or side length C, I am going to have to use the law of sines. Okay, so let's focus on A. Right, so the law of sines tells me that side length A divided by the sine of alpha is equal to side length B over the sine of beta is equal to C over the sine of gamma. All right, so I'm looking for side length A. I know alpha. What else do I know? I know gamma. I know beta. And I know side length B. Okay, so you only ever want to use two parts of this equation, and you want to use two parts where you know everything but one thing. All right, so I'm going to use the A and B part of that equation. All right, so I'm going to say I want A, I know alpha, 49 degrees. I know B is 27.4. Oops. And I know beta. Beta is 28.7. All right, so I know everything in that formula except for side length A. All right, and we're just going to use algebra to solve for this. Okay, I want to solve for A, so I'm going to multiply both sides by sine 49. All right, and that allows that to cancel out. And then I'll just have A equals 27.4 sine 49 over sine 28.7. All right, we're just going to type that in wholesale to the calculator, making sure you're in degree mode, otherwise you'll get the wrong answer. All right, and I get 43.06 change. Let's see, I'm going to round that off to 43.1. Okay, so now I know side length A. And then you're going to do the same thing to solve for side length C. We're going to use the law of sines again. And again, we can't rely on anything that we know, the SOHCAHTOA or the Pythagorean theorem. You're stuck with the law of sines or the law of cosines, which we'll do in the next section. All right, so I'm going to do the same thing. Let's get rid of all this stuff here. All right, for side length C, again, I'm just going to copy down the law of sines. All right, and again, if I'm looking for C, I'm looking for C. I know gamma. All right, and I know everything else in the triangle. I know B, I know beta, I've solved for A, and I know alpha. I'm actually going to use that part of the law of sines because I do know side length A, but I actually rounded off in order to get it. So I'm going to use this part. And you could use either one. You're going to get the same answer if you choose to use A and alpha instead. All right, so I'm going to plug into this part of the formula. I'm going to do B over sine beta equals C that I don't know over sine gamma, 102.3. All right, and then I'm going to multiply both sides. I'm going to solve for C, so I'm going to multiply by sine 102.3 102.3. And that gives me C equals sine 102.3 times 27.4. Again, that went into the top of the fraction because this sine 102.3 is really over 1, so I'm just multiplying fractions there. Okay, so I go to my calculator, 27.4 sine 102.3 divide by sine 28.7, and I get 55.7. All right, and that's my third side length. Okay, and those were the three things that I was solving for in my triangle. All right, and in reality, when we do a word problem, we're only going to want probably one of the three things that we don't know, but that's our first example. All right, so example 2 tells us the bell tower of the cathedral in Pisa, Italy leans 5.6 degrees from vertical. A tourist stands 105 meters from its base with the tower leaning directly toward her. She measures the angle of elevation to the top of the tower to be 29.2 degrees, and we are to find the length of the tower to the nearest meter without Googling it. Okay, so we have the Leaning Tower of Pisa. So there's the ground, and here's a building that is definitely not perpendicular to the ground. All right, and they tell us that this tower leans 5.6 degrees from vertical. All right, so that 5.6 degrees, okay, there's the vertical. This is my 5.6 degrees. And then we have a tourist standing 105 meters from its base with the tower leaning directly towards her. So she's over here, 105 meters from the base. All right, and she measures the angle of elevation to the top of the tower to be 29.2. All right, so remember, angle of elevation is from horizontal number of degrees that we have to look up. Okay, so that's giving us this angle. All right, and the way I drew my diagram, clearly that's a lot bigger than 29.2 degrees, but as long as we label it correctly, we'll be all right. All right, and we are trying to solve for the length of the tower. Okay, so I'm going to call that x. That's the distance along this side of the tower. Okay. All right, so I have this angle, 29.2 degrees, and it's across the side length that I'm looking for. So in the law of sines, I'm going to be able to write x divided by the sine of 29.2 degrees, and that's going to be equal to some other side length and angle ratio. Now, the only other side length that I know is this 105 meters down here, so that's going to have to be the side length that I use, okay, in my law of sines, which means I really need to know the angle that's across from it. So I really need to know this angle up here. All right, the only other angle information I have, though, is that 5.6 degrees. All right, so how am I going to get from there to the angle that I want? All right, so I'm going to use the fact that the ground and this perpendicular dotted line that I've used make 90-degree angle. And so that means this angle down here, I can figure that out. That's going to be 90 minus 5.6 degrees. That gives me 84.4 degrees. Okay, and then I can use that to figure out my top angle up here. Okay, so that this angle can be 180 degrees for the whole triangle. We've used up 29.2, and we've used up 84.4. So 180 minus 29.2 minus 84.4. That leaves me 66.4. All right, so that is the other angle that I need in my law of sines. Because remember, whatever side length, this 105 that I'm using, I need the angle directly across from it, opposite it. So I'm going to say sine of 66.4. All right. And then we can just use our algebra to solve for x. I'm going to multiply both sides by sine 29.2 times sine 29.2 to solve for x. So again, multiplying fractions here. I'm going to get 105 sine 29.2 divided by sine 66.4. And I get 55.9. And again, that x was the length of the tower, and it's going to inherit those meter units from the 105 meters that were given in the problem. All right. Okay, so one more word problem. Example 3. This one gives us the picture. Okay, so the diagram shows a blimp flying over a football stadium. Find the height of the blimp if the angle of elevation at the southern end zone, point A, is 70 degrees, and the angle of elevation from the northern end zone, point B, is 62 degrees. And the distance between the viewing points of the two end zones is 145 yards. Okay, so we are looking for the height of this blimp. So that's actually going to be, let's just draw that with a solid line. That's going to drop a perpendicular to the ground. So that is the x that I'm interested in. All right, and actually that side length is in a right triangle. Okay, so that particular triangle, we could use SOHCAHTOA, we could use the Pythagorean theorem, whatever we wanted to do. Right? But I only have this angle 62 degrees there and then an unknown side. Okay, so if I was going to use, that's the opposite side. So if I wanted to use sine, I would need opposite over hypotenuse. That means I need to know that side length there. If I wanted to use tangent, I'd have to use tangent 62 equals opposite over adjacent. I would need this side length down here, the adjacent, and I don't have those. All right. Okay, so I would like I said, I would like to know what this hypotenuse is over here. All right, so I'm going to call that h for my hypotenuse of my right triangle. If I know that, then I can use sine equals opposite over hypotenuse to find the side length that I'm looking for. All right, so now if I kind of zoom out and look at the oblique triangle that the blimp and the end zones are a part of, I can use the law of sines on that. It's not going to tell me x. All right, so let's see, kind of get rid of that one here. So back here, let's see what I can figure out. If I can solve for that h, then I can go back and think about how high the blimp is off the ground. Okay, so I have h, and that's across from angle 70 degrees. So in the law of sines, I can say h divided by sine 70. Let's see, the only other side length that I know is this 145 yards down here, so it would have to be 145 yards. But then I would need to divide that by the sine of this angle up here. All right, but that one I can figure out. I already know two angles in this triangle, so I could just figure out 180 minus 70 minus 62. That's 48 degrees. Okay, so I can use that as my angle that's across 145 yards. Okay, so it's going to be sine 48. All right, and then I can just multiply both sides by sine 70. And that gives me my h. All right, so again, sine 70 over 1, just multiplying fractions. 145 sine 70 divided by sine 48. and I get 183.3. All right, so that's the length of that side of the triangle. But if we remember back at the beginning, the whole point of this, we were trying to find this height, x, of my blimp when I drew that right triangle. Okay, so now I'm focusing on just that part of the diagram, that right triangle. All right, so now I can use my SOHCAHTOA. I've got this 62-degree angle here for SOHCAHTOA. Sine of 62 degrees, we'll come do this over on the right here, sine 62 degrees equals opposite over hypotenuse. And I can use that again because this right angle, the perpendicular. So I'm back to using right triangle trigonometry. Sine is opposite, which is that x, over hypotenuse, which I just solved for using the law of sines. Then I can just multiply both sides by 183.3. to solve for x. So x is going to be 183.3 times the sine of 62. And I get 161.8. All right, and so word problem, so I need some units. My distance, so x is a distance, so I'm going to use the distance unit. That's 161.8 yards. It's the altitude of our blimp. Okay, so again, law of sines, we're only going to use that version. Again, make sure you add this to your, your note card or your identity sheet. A over sine alpha equals B over sine beta equals C over sine gamma. All right, again, we're using that just to solve oblique triangle situations where two angles and a side not between them. That would have been the last one. Or two angles and the side between them. That's what we had in this problem. All right, and the law of sines will solve those triangles for you. All right. That's it for now.